Hi everyone, welcome back to my video on control systems. In this video, I'm going to demonstrate how do we sketch the Bode plot by hand of some simple components derived from a transfer function. From the previous video, we understand that the Bode plot comprises of two subplots. One is the magnitude, another one is the phase shift that changes according to the varying frequencies. To sketch both plots, we have to break down the transfer function that we see into a smaller components. And there are basically four components that we have to observe here. The first one is the gain, second one is the integrator or derivative, the next one is the first order pole or zero, and the last one will be the second order complex pole or zeros. Let's move to the first one, a simple gain k. But before we do this, we need to make sure a few terms correct. Now, if we let the complex term q is equals to a plus jb, where a is the real part and b is the complex part. To find out the magnitude in this case here, we'll be using 20 log the magnitude of q, which is equivalent to 20 log square root of a squared plus b squared. If you would like to find out the phase of q, that will be equals to inverse tangent of the complex part b divided by a. Okay, let's begin on the first step. The first component that we will be looking at here will be the k. And basically k is just a simple gain. And the magnitude of it will be the magnitude of g will be 20 log k dB. And the phase of g will be inverse tangent. And since k is always real, it will be 0 divided by k. So we have 0 degree. In the sketching here, we can say that in our magnitude plot will be just one straight line across all frequencies with a value of 20 log k. While phase, we are going to observe always will be 0 degree. And that's all for the simple gain k. Next, we move on to the integrator or derivative. For this example here, I'm going to assume that it is 1 over s. The 1 over s will be transformed to 1 over j omega when we are dealing with the frequency response. The magnitude of g will be equals to 20 log the magnitude of 1 over j omega. Because of the complex term j omega lies in the denominator, this term will become negative 20 log omega. And to ease our drawing, we are going to take the omega in the range of d, where d it is the decade. Decade takes the value of a multiple of 10. And the magnitude of g will become negative 20 log d. And because of the log is base of 10 and d is multiple of 10, and this will become a straight line with a negative 20 dB per decade of slope. As for the phase of g, and since the j omega is a purely imaginary term lies in the denominator, this will become straight away negative 90 degree. And when we transform these expressions into drawings, first we look at the magnitude of g. The magnitude of g is a straight line having a slope of negative 20 dB per decade. And it will cross 0 when the omega is equals to 1. So it will be at 0 point here. And basically for each decade, you're going to drop by negative 20, negative 20. So the next decade will be probably here, which is drop negative 20 dB. And the next one will be here. So if you project this line, basically we will form our magnitude plot. You can see that the line will be somewhat like this. Okay. As for the phase, will be a constant negative 90 degree. So this will be negative 90 degree, and for the straight line above will be negative 20 dB per decade. So that will be for 1 over s, our integrator. As for the derivative, which is a reverse of it, basically we are going to look at the same line, but the slope will be going up by positive 20 dB per decade. And for the phase shift, this is negative 90, but for derivative, it will become positive 90 degree. Okay, so let's move on to the first order pole or zero. For the drawing here, I'm going to assume that the first order pole with a form of j omega over omega n plus 1. In this form, the magnitude of g will become 20 log the magnitude of 1 over j omega n plus 1, and this will become negative 20 log square root of omega over omega n square plus 1 square. We are going to assume that the omega lies in two different range. The first one is omega is very less than compared to omega n. So in this case, it is not hard to observe that this entire term will become 1, and anything log 1 will become 0. Therefore, in this range, my magnitude will become 0 dB. And the next range should be, of course, when omega is greater than omega n. And for the sake of the drawing here, we are going to set omega is equals to d times of omega n, where d will be also the same as previous, the decades, which is a multiple of 10. And when we substitute this into the expression for magnitude, the magnitude will become negative 20 log d. And the 1 here will be ignored simply because d is always much greater than 1. So we can say that this term will transform into a drawing of approximately negative 20 dB per decade as well, similar to the previous example. For the phase of g, it will become the phase of 1 over j omega over omega n plus 1, and this will become 0 minus inverse tangent of omega over omega n divided by 1, which is inverse tangent of omega divided by omega n. We are going to assume three cases over here. The first case here is that when omega is 10 times smaller than omega n, or somewhat even smaller. And next, omega will be equals to omega n. Omega is 10 times of omega n. When omega is much smaller than omega n, let's say 10 times smaller, by substituting this relation back into the expression for phase, we can actually observe that my phase will become 1 over 10. Minus. And this will give us approximately equals to 0 degree. When omega is equals to omega n, the inverse tangent terms here will become 1, and minus inverse tangent of 1, our phase will be equals to minus 45. And when omega is equals to 10 times of omega n, or somewhat even larger, by substituting this back into this ratio here, we can get the phase of g close to negative 90 degree. Okay, so let's draw this out. For the magnitude plot, if we say this point is our omega n, this point will be 10 times smaller than omega n, and this point will be 10 times larger than omega n. For the magnitude plot, anything before omega n, it will be a straight line of 0 dB. And anything after omega n will be one straight line with a slope of negative 20 dB per decade. So at 10 times of omega n, this will be negative 20. And we just connect the line. And that will be our sketch for magnitude plot. For the phase plot, there will be 3 points. 10 times smaller than omega n will be 0. When omega equals to omega n will be negative 45. When omega equals to 10 times of omega n will be minus 90. And since this is just an approximation, we are going to use straight line to connect all this. And here will be our plot for first order pole. Similar to the previous example, for the first order 0, everything will be just the flip upon the 0 axis. Next, we move to the last term, which is complex poles or zeros. In this example, I'm going to assume the complex poles having the form of 1 plus j 2 zeta omega over omega n plus j omega over omega n squared. While the plots is greatly depending on the value of the zeta, we are going to use a simple approximation over here, which by using the principles that we have introduced earlier for the first order pole, we can simplify the expressions of the g becoming a straight line of negative 40 dB per decade after omega n. And for the phase of g will be equals to 0 degree when omega equals to 10 times of omega n, negative 90 when omega equals to omega n, and negative 180 for omega equals to 10 times of omega n. You can observe that all numbers over here are basically just a double of the first order pole. And using the same place as earlier, this is our omega n, this is 10 times smaller than omega n, and this point will be the 10 times of omega n. And at omega n, it will be 0. And anything before that will be 0 dB. And after that, each of the decades will be dropped by negative 40. So at 10 omega n will be here and connect straight line. As for the phase plot, 10 times smaller than omega n will be 0, omega n will be negative 90, 10 omega n will be negative 180. And similarly, we are going to use a straight line to approximate it. And of course, earlier we said that it will be greatly depending on the zeta value. So we could observe that this is merely an approximation. In the real case, when zeta is sufficiently small, we will be observing a line of something like this, where this point here will be our resonant frequencies. Okay, that's all that I want to show in this video. In the next video, I'm going to work on an example of how do we combine all these individual components into one complete Bode plot sketch. Thanks for watching. Bye.